Hi, guys. I wanted to give you a couple of options for being successful with today's reading. One of those options is go ahead and open the PDF and read the document yourself. Another option could be open the PDF and listen to this recording um, of the reading, and the other option could be just listen to the recording. So I know that some of you learn better from listening, some of you learn better than reading. You choose how you want to proceed. Activity 12, the electromagnetic spectrum. Sunlight is a combination of light of various frequencies. Some of the frequencies can be seen and some cannot be seen by the human eye. The reading in this activity explores the nature of these waves, which are electromagnetic. An electromagnetic wave transmits energy across distance as moving electrical and magnetic fields. Just remember, not long ago, we studied electric fields and we studied magnetic fields, and we noticed that there was positive and negative, that the energy, that the field lines flowed from positive to negative. And so those those two fields, the electrical and magnetic field, interact to move energy. Our guiding question today: what are the characteristics of electromagnetic waves? And the materials that you'll need, I've actually linked it to the to the Google assignment, is student sheet, which is the anticipation guide. And I'm just doing this honor system. Open the anticipation guide, look through the questions. What do you think? Read the information, look back at the questions. What do you think? The assignment for this, you will need to submit an answer to the one question that is linked to the Google assignment. This image that you see here shows one wavelength of ultraviolet given off by the sun. The wavelength is not visible to the human eye, but is typically colorized in blue. To make waves visible that are not, we manipulate and modify them with computers. Here's the reading. Herschel's famous experiment. In 1800, British astronomer Sir Frederick William Herschel made a big discovery. While looking at the sun through colored lenses, he noted that some colors of light felt warmer than others. He wanted to learn more. He designed an experiment to try to measure the temperatures of the different colors of light. In this experiment, Herschel used a prism, or a triangular piece of glass, to refract sunlight into the colors of the rainbow. When white light travels through a prism, each wavelength refracts a slightly different amount, creating a rainbow. Herschel first separated the light, then he placed thermometers such that they were only struck by one color at a time. He noticed the red light caused greater temperature rise than the green or violet light, as shown in the diagram on the right. So here's his experimental setup, Herschel's experiment. He's got his prism. The sun is coming through this tiny little slit, right? So how do I really focus? That experiment that we did the other day virtually with the light box, that slit of light was coming out. We were watching whether the slit, that narrow beam, was going to reflect or refract. So with sunlight in the prism, that narrow beam of light actually refracts differently depending on the wavelength, and white sunlight is all colors together that we can separate with these refractions. And so he set up the thermometers in the different regions of the color. Really cool experiment. And he collected some data. To his surprise, he also noticed that the temperature rose even more when the thermometer was in the unlit area just below the red end of the spectrum. Based on his results, Herschel reasoned that sunlight must contain invisible energy that can heat up objects. He called the energy calorific rays, since calorific refers to heat, like calories is the amount of heat for something. When he carried out other tests, Herschel found that calorific rays behaved just like visible light. They could be reflected, absorbed, or transmitted like waves. Because the wavelength was just longer than visible red light, scientists in 1881 named this kind of light infrared. This name was chosen because of the prefix infra means below. The discovery made Herschel the first person to detect a type of electromagnetic wave not visible to humans. You guys, this was 1800s. That's crazy. Infrared heats up objects more than visible light because of its wavelength. When infrared hits an object, the molecules in the object often absorb infrared. The result is an increase in the molecule's energy, which makes the molecules move faster. Faster molecules lead to a warmer object. Not only do most objects readily absorb infrared, but warm objects also give it off. In a separate process, warm objects will radiate infrared and other wavelengths of electromagnetic energy. So the night glasses technology that detects infrared wave in the pitch dark because of the heat coming off. So I can tell where warm objects are, aka lions hunting at night, aka humans slinking around during wartime. That is really cool. The other thing that you should watch is, I think it's called Night on Earth. And it's a new documentary series on Netflix that this technology has gotten so good. They have cheetahs hunting at night, and it's awesome with this wavelength technology. As our computers get better, we can see things that we could not see before because the wavelengths were outside the visible light. Ultraviolet energy. A year after the discovery of infrared, Johann Wilhelm Ritter in Germany decided to find out if there was energy beyond the violet end of the visible spectrum. Herschel didn't think about doing that because you're so focused. He carried out an experiment like Herschel's. Instead of a thermometer, he aimed the light onto a special paper that turned black when exposed to light. The chemical on the paper, silver chloride, darkens more when hit by light from the violet end of the spectrum. When Ritter separated the light, the paper turned darkest just beyond the visible violet end of the spectrum. He first called his discovery chemical rays after the chemical reaction in paper. Later, this type of light, just beyond the visible light spectrum, became known as ultraviolet because ultra means beyond. Ritter's results stayed the same when he changed the amount of light shined on the paper. Reducing the brightness of the light is similar to reducing the intensity of a sound wave. Yet, no matter how much Ritter dimmed the light, the paper turned black. This is because the reaction in the paper was due to the wavelength of the ultraviolet and not its brightness. Longer wavelength light of any brightness, such as visible light or infrared, does not turn the paper black. Remember the difference between wavelength, which is the frequency of how many waves, and the brightness is amplitude. So I can change that amplitude of brightness, but it's the wavelength that changes this silver chloride. Photons are the tiny light particles that make up all electromagnetic energy. The amount of energy that a photon carries depends on its wavelength. Short wavelength light carries more energy per photon than longer wavelength light. For example, ultraviolet carries more energy per photon than infrared and visible light. In fact, ultraviolet photons have the most energy of all the electromagnetic energy that commonly reaches the Earth's surface. Ultraviolet energy can be helpful to Ultraviolet energy can be helpful to humans. When human skin is exposed to ultraviolet energy, the body converts a chemical in the skin into vitamin D. Vitamin D is necessary for bone growth. Those people who lack sun exposure and whose diet lacks vitamin D may develop a deficiency. This results in bone growth problems in children or soft bones in adults. Some people also suffer from a type of depression called seasonal affective disorder when they don't spend enough time in the sun. One more benefit of ultraviolet is that it can be used to disinfect medical devices. The wavelength range of ultraviolet has enough energy to destroy bacteria, viruses, and molds. At the same time, ultraviolet energy poses a danger to people and other living things. Its wavelength causes damage to living cells. Over time, it can result in skin cancers and cataracts, like those in Tia Anna's eyes. That was from a previous reading. She was suffering with cataracts. Ultraviolet also causes some fabrics and materials, such as those used in clothes, furniture, and car interiors, to fade and become brittle. You know, when you go camping and you take I can't remember what it's called, it's like a steri stick, or you put the water in the container and there's this tube with light in it and you turn it on and it has UV energy that you just kind of wave around in the water and it disinfects the water. It kills that bacteria and viruses. That's a similar concept. Light from the sun. Herschel and Ritter's experiments showed that sunlight contains more energy than meets the eye. As shown in the diagram below, most of the energy that reaches Earth is in the form of infrared, visible and ultraviolet light rays. The diagram also shows that much of the energy given off by the sun never reaches Earth's surface. The gases of Earth's atmosphere reflect and absorb some of the energy. The atmosphere acts as a shield that protects all living things from most of the very dangerous short wavelength, high energy ultraviolet X-rays and gamma rays. Although ultraviolet has less energy than other short wavelength waves, like gamma rays and X-rays, they pose more of a hazard to living things because more ultraviolet reaches the Earth's surface. If Earth's atmosphere did not have a thick atmosphere, much more electromagnetic energy would reach Earth's surface, causing more harm to living things. So you'll see at the top of the Earth's atmosphere, here in blue, our y-axis is spectral irradiance, watts per meter squared. So that's like like how in this area, how much energy in the watts. And then these are the different wavelengths of light. So the longer, 500, short. 500 is a short wavelength, high frequency short wavelength. Those short wavelengths at the top of the atmosphere are almost double the energy. So that Earth's atmosphere is protecting those shorter wavelengths from getting to us on the Earth's surface. As you get out into the longer wavelengths, those really low frequencies, there's just not much out there from the sun. And this is the sun. So the sun's energy that's coming to us is pretty high energy. The electromagnetic spectrum. In addition to infrared, visible, and ultraviolet, the sun emits a large amount of other kinds of invisible electromagnetic energies. They include radio waves, microwaves, X-rays, and gamma rays. Together, the continuous range of all possible electromagnetic wavelengths makes up the electromagnetic spectrum shown below. I love this diagram. Although ranges of wavelength in the electromagnetic spectrum are given specific names such as radio, visible, X-rays, the categories overlap. This is because it is often hard to distinguish where one group of wavelengths ends and the next one begins. This is a fluid spectrum. In fact, all electromagnetic energy has certain common traits. For example, all electromagnetic waves can travel through a medium or through a vacuum. No medium, no particles. They can all be reflected, absorbed, and transmitted through various materials. The degree to which each type will reflect, absorb, or transmit depends on the wavelength of the wave and the surface or material it hits. For example, electromagnetic energy with the wavelength of microwaves is readily absorbed by water, but not other common materials. This is why water heats up quickly when it's placed in a microwave. Although electromagnetic waves have many things in common, there is a huge difference in wavelength from one end of the spectrum to the other. The range of wavelength from gamma rays to typical radio waves is over 1,000 meters. Each range has some unique characteristics. Electromagnetic waves with shorter wavelengths, higher frequencies, carry more energy than those with longer wavelengths, lower frequencies. This is why waves from ultraviolet to gamma can penetrate living cells and damage them. Longer wavelengths of energies, like those in the radio range, can be generated or received by an antenna. Human eyes can only detect a very small range of wavelengths from about 380 to 750 nanometers. And a nanometer is 1 billionth of a meter. So I love looking at this diagram, and it's colorful and it tells a lot of really great information. So we see these categories of the different kinds of waves. We see their wavelengths. We see what they look like graphically, and we see the comparison of how long these wavelengths are, and then also the frequencies. And you'll see right in here is my visible light spectrum. Electromagnetic energy and sound energy. In many ways, visible light waves and all other types of electromagnetic waves behave much like sound waves. However, there are some very significant differences. Sound requires a medium through which it is transmitted, but electromagnetic energy does not and can therefore be transmitted through a vacuum. This is why sunlight is able to travel from the sun to the earth. But outer space is utterly void of sound, because light waves do not require the presence of atoms or molecules to be transmitted. They are not considered to be mechanical waves. Light is a transverse wave that carries electromagnetic energy. Electromagnetic waves also travel much faster than sound waves, as shown in the table below. Here's what my brain doesn't like, but because it's something that I'm like, what? I will remember it. So remember when we were studying longitudinal sound waves, compression waves, we learned that when those waves that are moving parallel to the direction of energy, when they're moving through a medium, the denser the medium, the faster I could move. You guys, that's not true for electromagnetic. Electromagnetic waves are different. Electromagnetic waves travel the fastest in a vacuum. So if we look at the speed of light, and so you've heard of light years, how many light years is it going to take? How many years light years did it take for that light from Betelgeuse to reach the Earth? How far away is it? How old is Betelgeuse? When did that light leave? That's all because light in space travels at about 300 million meters per second. Air, light travels almost as fast. In a vacuum, speed doesn't travel at all. I can't move my compression waves, but in air it travels at 344 meters per second. Speed of sound in air compared to the speed of light. Look at those differences and think of a situation that you know for sure really well that shows you the differences between those waves, thunder and lightning. That lightning you see first because it travels so fast, and then later you hear the sound. Extending our senses with electromagnetic energy. We use electromagnetic waves in many ways in our daily lives. For example, we use X-rays to scan bones and teeth. Some remote controls send infrared signals to control devices such as TVs. Wireless internet connections rely on radio or microwaves to send and receive data. Microwave ovens transmit microwave energy to the water and food, thereby heating it. Electromagnetic waves allows us to extend our senses. One way is through infrared imaging in night vision goggles. Night vision technology lets us see objects by changing the infrared rays given off by objects into an image we can see. Since warm bodies give off infrared energy, a person wearing night vision goggles can scan an area to see people with other warm-blooded animals in darkness. Additionally, there are tools that can sense various ranges of electromagnetic energy. For example, astronomers use radio telescopes that detect radio waves. Astronomers use these telescopes to see distant objects in the universe. Remember the black hole story. So on this page, page 17, you'll see a picture of a radio telescope that is gathering radio wave data from wherever it's coming from. And then they're going to manipulate that data via computer technology, either into sound or something that your brain can see. So we talked about Herschel and the experiments he did. We talked about Ritter and the experiments he did. This will definitely come back up for you in physics in high school. We looked at infrared and ultraviolet and how they were alike and similars. We had so from the following list, choose an option that describes the portion of the range of electromagnetic waves that's visible. And so, on that electromagnetic spectrum, how much of the spectrum is visible light? Obviously really small. And then talking about higher frequencies, ultraviolet with Tina's cataracts. So now we're going to go back to our post here and look at the question. Now that we've collected some data and seen a few labs, it is time to stop and digest. Today you will do the following. Read over the anticipation guide, Waves, Act 12, _SS, and think about the questions. Where are your thoughts now? If you'd like to write down your thoughts in your student notebook, that would be helpful to your brain. Then you're going to read Activity 12. I just read that to you. You can read it to yourself. We talked about those options. And if you'd like to pause and take notes, great. You do that in your student notebook. Then go back to the anticipation guide and review the questions. Have your thoughts changed? How have they changed? And just think about this one to prepare and think about this question and prepare an answer to submit. You're going to write and submit your response to the question, how has your knowledge grown from before the reading to after? What did you learn? Be specific. For example, instead of saying, I learned about the electromagnetic spectrum, you need to describe exactly something that you learned. You are now synthesizing that information and telling me and describing it to me as if I don't know it, and you're going to help me learn it. I hope this was awesomely enjoyable to learn all new content, and I will talk to you soon.